Okay, welcome back everybody. I'm just going to recap this real quick, give us one more chance to see that this answer right here, when we're doing inference on the mean, without knowledge of variance or the precision, we don't have it in hand, this is going to be a t-distribution if we do the conjugate analysis. So you could do that for any conjugate analysis and get a t back. So normals, gammas, we did the limit of the conjugate analysis to kind of wipe out the hyperparameters. It wouldn't be uncommon for me to ask you to do the full-blown thing on a midterm. So you should try to do it anyway. Make sure you get back to the same answer when you set alpha and beta equal to 0 and the variance in the hyperparameter off to infinity. Just like.
But you said you could do any conjugate analysis and then a t for that?
This one, for this example that we're working on. So there's only one conjugate analysis, right? There's gamma for the precision,
okay,
normal for the mean.
Regardless.
Yeah, I don't mean it in general, anything you do. So this had a specific likelihood in here. And the likelihood, once we had the likelihood, there were no choices. So the likelihood drove all our choices. It let us know what was conjugate in the first place. So we had to account for model form to know all of that. Yeah, so make too much generality specifically for this example. Sigma squared is equal to 1 over phi, however you want to parameterize it. It's all the same. So we like to deal with this so that the conjugate prior is a gamma. If we dealt with this, the conjugate prior would be an inverse gamma. So it would all work out the same and we'd still get a t at the end of the day. So if you want an exercise in normalizing constants, you'll go through that. So I don't know if that would help you in this class. But it wouldn't be uncommon for me to say, let the priors be a normal mu naught, sigma naught squared, and this one, pi phi, would be some gamma. I'll use alpha and beta here and say, do the whole calculation right here. And let me see where your hyperparameters pop out. I made this really easy and let that go off to infinity, which meant that this meant nothing. So that disappears from the normal because we flattened it all out. And I ended up letting that be 0 and 0. So this thing right here was proportional to 1. This is proportional to 1 over phi. So that's the analysis we did. So people are always asking me for extra practice problems. They're built into the problems we already have on board. So I probably won't do anything too surprising come midterm time. But you should probably be filling in some of these side calculations. The homework help you to do that as well. Okay, so this right here is a t-distribution. And I find that completely unsurprising because that's what I learned in Stat 101 and Stat 101.1 and Stat 101.2. This was always true. When you're doing inference on the mean and you don't know what the variance is, you always look things up in a t-table. You did maybe a t-test or something like that. We're not talking about hypothesis testing yet. So, but all of those tests are built off of a t-distribution. So what you probably should have asked yourself a long time ago when you're doing all these tests is, what does this distribution look like? So I wish we started there in statistics so we got a grasp of what we were doing. Anyway, turns out Bayesian ends up doing things based off of the exact same distribution that our non-Bayesian friends also do everything off of. And we'll re-encounter this later on when we do hypothesis testing, but we're just kind of deriving the distribution first. So this is the same distribution classicists use. This same distribution for one sample t-test. It's just a fact. We'll encounter this later on. This is supposed to remind you back when you did Stat 101, which I do assume everybody's done. Whether or not I was in high school or college at some point, I would be hard pressed to think that you never took a statistics class and you jumped into this one. Am I wrong about that? Sweet, I'm gonna hold you to that. So, okay, let's just go back through this real quickly. What did we do? We wrote this down up to proportionality. So I ended up using the likelihood. And then I used this prior, and I used that prior. So yeah, a priori, we used independent priors. There is way more to this discussion and higher dimensions and all of that, where you can use different forms of priors, and there's 100-page papers that are written on this. So there's thousands of them. So the literature is millions of pages on how to elicit and come up with priors, how to choose priors for different reasons. And the conversation goes something like this. It depends on what you want to know. So that will always be true. So we're just starting the conversation somewhere where at least these principles haven't failed us yet. I assure you that all of these big wigs that have come up with all of this theory in different situations, they looked at examples where things went wrong to gain their inspiration. I promise you that. So we know all these guys still, they're still alive. So all of them are. They came up with this stuff. They still work at universities. So you can even go talk to them about it. So I promise you. They saw things go wrong in the 70s and they said, how do we fix it? So when they were young assistant professors and grad students. Okay. Anyway, nothing is going wrong so far. We'll encounter problems later on when we get to hypothesis testing and disagreements. So this right here is just going to be the integral, 0 to infinity, phi to the n over 2 minus 1, e to the, this is the prior, so this part is the contribution from the likelihood, e to the minus phi sum xi minus mu squared over 2. d phi. So that's the integral that we're solving to get this distribution. We've written this down up to proportionality. So we didn't normalize the integrand. We've already thrown all that stuff away just to make our lives easier. So we recognize this as a gamma. With 2 parameters. You recognize those parameters here. And you recognize instantly what this integral is. It's the inverse normalizing constant for that gamma. So this looks like gamma alpha tilde, beta tilde alpha tilde. And so this right here is a constant right here because it only involves n and not any parameters in there. So they're just numbers. So this thing is just proportional to beta tilde minus alpha tilde. If you can do that quickly in a couple weeks' time, you'll feel really good on the midterm. You should do it just like that. Bam, that's your answer. If you're not there, you should practice this problem until you get there and go, I can just recognize what this integral is. So answers this thing. So now we're in cruise control. So we're not even thinking about stuff. Now we'll start plugging things in and be a little bit more careful. So this is going to look like sum of the xi's minus mu squared over 2 to the minus n over 2. Right here. So there's our answer. We know this thing looks like a t, so we need to make it look like this thing. We know where this thing is centered. You've probably done that little mini calculus problem already by figuring out where some of the squared things are centered. So it's centered at the average every single time. So we gained some inspiration on how to solve this right here, that we rewrote this as sum of the xi's minus x bar plus x bar minus mu, still all squared. We got rid of this 2, doesn't help us. We need to write this all to the minus n over 2. So cut in some braces. It expand the square, notice that the cross term cancels. It's 0. So all stuff you'll be able to do real quickly after a couple iterations of practicing this. So this looks like this. Sum of the xi minus x bar squared. I goes from 1 to n plus n x bar minus mu squared to the minus n over 2. This is where we were last time, and we carried it through one more step. Anybody lost? Or is this just getting fast? So we're just on repeat. So this was all last time. We're just kind of mimicking the speed you would want to be at when you're doing a midterm. So give ourselves a little bit more room to clean up this answer. So this, I'm going to write up the proportionality by factoring this thing out. I'm going to do it one step in my head. If you want to see all the steps, go back to the lecture from last time. So we're very careful about this. But this is proportional to 1 plus n x bar minus mu squared over sum of the xi's minus x bar squared. I goes from 1 to n to the minus n over 2. So we factorized out one of those things that was in the denominator, raised to whatever power it was. Again, that was all a constant, so I could chuck it. So all we factorized out was a form of that right there. It doesn't have any mu's in there, which is my random variable of interest. If I start factorizing things that depend on mu and throwing them away, I throw away the random variable, the thing that has shape in the equation. So doing things all the way up to proportionality is helpful. You don't have to just keep renormalizing things all the time. So we'll rewrite this out just a little bit differently. I'm going to rewrite it like this. I recognize where the degrees of freedom should be. So this is n minus 1 plus 1 divided by 2. That's still n over 2. Be really clear about this. This is the degree of freedom. I know this by heart. I can never forget it. I know where the degree of freedom is. If you have a hard time remembering this, you will not be able to use a note card, any notes in class. I expect you to remember it. So if you are that dedicated to go down to a shop in town and have them help you out, I'll allow that. So you can tattoo it on yourself, but that's it. No Sharpies allowed. I want permanence. So probably better to just remember this. So what this form looks like. So another distribution you'll keep coming back to in this class. So I recognize the degree of freedom there. I don't see that degree of freedom in here, so I'm just going to put it there. Make my life easy and just rewrite this into the scale parameter. So there was an n up here. I got rid of it a little bit prematurely. I erased it and forgot to do something with it. And I'll just put that n down here. I'll write it like this. Probably the worst way possible. I apologize to my third grade teacher. So I'm doing it for a reason. I like it like this. So this thing we recognize, maybe, this is usually called s squared, right here. So s squared is a typical estimator for the variance. Estimates variance. So I'll just write it out. If you've ever taken a stat class before, you already had this conversation, you've seen that. So usually they tell you this is a great estimator for variance. A lot of times we write it like this. So sigma squared hat to emphasize it's an estimator of sigma squared. And it has some cool properties. Probably the most popular property to cite is that it's the unbiased estimator of variance. You can quibble over whether or not this is a good reason to like this estimator. If you've taken my inference class before, you know I have other favorite variances, but if that's what we're arguing about, we have bigger problems. So, question, you like this one or that one? I understand degrees of freedom, I understand geometry, I understand arguments. I also understand that this is closer on average. This is the MLE. So it turns out it has lower variance than that estimator, and it makes up for the deficiency in bias. So on average, it's closer. So some people like this. This is a psychological trick, I think. Anyway, regardless of all that stuff we know, it pops up in the Bayesian estimator too, so maybe that makes us feel solid. You're like, it's okay. Assuming all these priors right here, likelihood we didn't assume anything about taking a Bayesian lens to the problem, I see that same estimator. So maybe we're back to liking it for a minute. So our answer at the end of the day is our location parameter is always right here. Keep in mind, my random variable and all of these sort of aside conversations is z. So we want to look over to the left, to the right of z. We're probably going to need to spin this around. This is the random variable in this equation. So that was this thing right here. So I like to turn this thing around, make it look like that. So this is the location parameter. That's the location. This right here, this is the scale squared. I usually just say scale parameter, the variance sort of thing. Turns out it's not always a variance in a t-distribution. Sometimes we can consider it a variance. Can somebody tell me what the requirement is that I can call that sigma squared thing a variance? Okay, let me ask a slightly different question, just since we're getting used to t-distributions. When can I call that a mean? I call that a location, it's where it's centered. Sometimes it's actually the mean, and sometimes in a t-distribution, the mean doesn't exist. That's why we use this other term to cover both bases. But sometimes it's an actual mean, it's the expectation of the distribution. But if you go to Wikipedia and look at a t-distribution, there's a requirement for the mean to exist, like in lots of distributions. What is it?
Degree of freedom is bigger than 1.
Bigger than 1. Yeah, so it's the degree of freedom is 1 plus epsilon for that to be a mean. That's true. The first moment only exists if the degree of freedom is bigger than 1. So 1 point epsilon will do it. So 1 plus epsilon. Same conversation. Probably think about the second moment. You know, when does a variance exist? It's when the second moment exists. If the second moment exists, the first moment will exist. They cascade that way. So when does the second moment exist for a t-distribution? Degree of freedom greater than 2. When does the kth moment of a t-distribution exist? When the degree of freedom is strictly larger than k. K plus epsilon will do it. We usually think of these in integers if we learn degrees of freedom from integers, but that whole concept can be extended. And I'm teaching this is just a knob that controls tail behavior, how fat those tails are. We don't have any special interpretation. If that bothers you, I will guarantee you don't understand variance either. Like, it's an abstract concept as well. Means and stuff like that, that's probably something that we feel like we understand. Maybe not means, but locations of things. Probably don't understand means very well either. So, but there's little things that we can use to bring peace to mind. Anyway, variance sometimes exists. We're not even thinking about that. Just scale parameter. Where is it? It's all of this stuff. So that's the scale. And I'll write that out as s squared divided by n. So this thing right here is estimating sigma squared, and this thing is converging to that. So it's converging to that. Law of large numbers, all of that good stuff. So, and the scale goes down by a factor of n as we see more and more data, and we become more and more precise. So that's why we like to see data, and that's like why we like to work with means and stuff like that, is it compresses our variance by a factor of n. So this gives us some comfort. So in expectation, this thing is precisely that, and I don't even need the limit. So this is exactly that thing. Asymptotically, as n gets bigger and bigger, it actually converges to it. So those are different statements. Sometimes they're the same thing. Okay, so that's all a recap. Any questions about all that? We'll revisit these sort of problems. We'll change the distribution pretty soon, but what I'd like to do first is add one more thing to this conversation and talk about how people forecast with things. And so we'll use the exact same problem. It's a very typical sort of problem. A lot of people induce normality, and they're kind of saying our answers around ellipses. So I like elliptical boundaries, you go for normals. So these are typical filtering problems work out this way. This would be the backbone for all of that, the foundations. So I'm not going to tell you all about filtering, but I'll give you at least the prelude to it and show you how to do basic forecasting. So let me prompt you with a question. Say you observe size coming from a normal distribution. In your mind, you might be thinking I could change that distribution, but I get to see data. So I get to see a collection of data. So you get to observe all of these, x1 to xn. So I'll just say y goes from 1 to n. Same statement right here. So you get this. And you want to know some data point in the future. I'll make this problem easy and say everything's IID. Everything I'm saying in this lecture extends to non-IID systems. You just have to have the right conditional structure in your likelihood. So as long as you condition correctly, and you write down your likelihood functions correctly, everything I say in this lecture is the exact same thing to dependent systems, so time series, for example. So there's nothing different about this, and I will give you a time series example in the future. Right now, let's just make it IID. You're missing nothing. So we want to know the future. And I'm going to call that x tilde, where this is a future observation. Just one day in the future. If this was a sequential system and there was dependence, I might say I've seen the last cap t days, and I want to see day t plus 1. And I need to induce all the dependent structure. But if you know what the likelihood is, everything I'm saying is still true. So I want to know someday in the future. What's a good answer? I've given you problem setup, so I wouldn't be willing to answer this question unless you gave me like, what is the data structure of the data? But since you've given me the structure of the data, I think I'd be willing to answer this question right away. X bar. So, answer, X bar. Not a bad answer. What else would it be? You know? Let's think about that later. Might not be so obvious. So why X bar? If it wasn't normal, I wouldn't necessarily say X bar. I'd say you assumed a ton of stuff. Since it's normal, we know normals are probably pretty well behaved. It's always X bar. But is this a good answer? I think if you're a statistician, this is a very lacking sort of answer that you want to know about uncertainties. You've got a lot of data, and I want to know how that scales to n, and I want to know kind of my distributional uncertainties around all of this. So, question, what's the variance? for the future. And I probably knew enough from whatever number of classical stat classes I'd taken to at least say, I could throw a guess out there. I remember my first stat class where they talked about this. I remember how they derived it. I remember what the answer was, and I remember it was intuitive after they derived it all. So what would a good answer be? S squared. So maybe S squared. Kind of like that. So answer, maybe. Let's keep this like highlighted right here. S squared. So probably you assumed you don't get to know that, and why would you get to know it? So let me just say maybe S squared if sigma squared not known. What if we knew sigma squared? So I'll say answer 2, sigma squared known. What would a good answer be? Sigma squared. That would be the analog of that answer. Is this a good answer?
You're asking what's the variance of that observation?
Yeah, I'm asking the variance of the future. Exactly. I think that's an incredibly astute thing to pick up on. Variance of what? You know? Variance of the future.
Of that observation.
Of that x tilde, this hypothetical thing that I'm thinking about. And I want to know what the future looks like, and I want to put some bounds on that thing. And if I can make probability statements, I'd like to do that as well. All that good stuff. So with probability whatever, we might speculate that the distribution of the future is probably normal. What else would it be? You know? So probably, if all the other data follows a normal distribution, it's not unreasonable to think it would be normal. We probably need to derive that and convince ourselves the math is clean on that statement. It is. So if we did a conjugate analysis, it would be normal. So we could definitely make it into something crazy by having crazy prior waves, but we'll make our lives easy. Any other possible answers? A3? You can play the same game, sigma squared known, sigma squared not known. Jared?
I mean, there are other variance estimators, so you could use some biased variance if the variance is unknown.
Fine.
Yeah.
Anybody else? Okay, let me just say one word, prediction intervals. This one I heard about at first. I took a regression class, and I remember prediction intervals coming up and prediction bands. There was a difference between the prediction interval just piecewise, so pointwise, is what I meant to say, and the bands for the whole regression bar, the variances for the regression estimators. They all have something to do with each other. They're all a little bit different. I know I'm not the only one that took a stat 101-esque regression class and remember something from it. Christiana?
I mean, the variance increases for prediction, right?
I would think so.
I don't remember how much.
So I was thinking of prediction intervals, but I guess I might be making a really naive mistake. I thought that for a confidence interval you're going to be using, that's like looking at x bar, variability x
Yeah.
bar, so it's like sigma squared over n.
Yeah.
And for a prediction interval, it's just an individual observation, so it's like sigma squared.
Yeah.
Maybe I'm forgetting what formula is.
Okay, yeah, maybe you are. So maybe you're remembering something. So what Josiah just said was the variability for this thing, how much does this kind of jitter around in space depending on which sample I've observed. If I went out and collected another n data points, this thing would bounce around. It wouldn't be exactly the same number. This has variance, x bar, and I'm thinking like a classicist by doing this.
We need to incorporate both the variability on our x bar and the variability of the individual.
So, yeah, exactly. So I've got uncertainty about how I'm estimating the center of everything in the first place. where everything is. So some variability is there. And then some variability is also in the future. And we know what the overall variance is of any data point, and the future data point is kind of like a data point. It is. It's IID. So I've got variability attributed there. So now we need to remember a formula to incorporate both variabilities. What formula? Multiply them together? Does that make sense? Exponentiate them? Sigma to the sigma?
For variance is so
Add. Normality variance is add. So, and I kind of remember, so maybe the answer for 3 is sigma squared plus sigma squared over n. So, or if I didn't know sigma squared, it's not unreasonable to think s squared plus s squared over n is a good answer. We will come to these answers. So I know I've provoked you a lot in all of these, but I think for this problem in forecasting in your old stat classes, they derive this. They're not Bayesians. We'll be Bayesians, and we'll rederive the same thing. So again, we're in the comfortable land of this class where everybody agrees, we just have different interpretations. And I kind of remember when I saw this, it was just like one of those like highlighted boxes in the middle of my undergrad book, and they just said things. And it was at a time in my life where I would go, that makes sense, moving on. I can remember that. You know? I have no problem remembering this. So it makes sense to me. I can even accept the argument, you know, variance is add. I'm good with that. Let's do that. Sam?
I'm a bit unclear on why we're able to add them.
Yeah, so maybe we're not good with that. Let's take a couple mathematical arguments, because some of you don't like intuitive. You only get intuitive after you go through the math, and I think that's fair. So we just were saying words, remembering things. Let's derive these. Sound fair? So variance is in normals. If I take normals and I add them together with each other, the variance is add, so maybe that intuition is extending. I don't think that's exactly right. So that's why we probably need to do some math. That's the way I remember it when I was taking a stat class for the first time. I only took a couple, and I was just skating through. This is easy. So back then. Now let's make it hard and actually reconstruct the real argument. Let's be Bayesians and do this problem and phrase it like a Bayesian will. We'll let this be a side, and then we can reconfront it and maybe talk about it a different way where you'll see these variances added in a very simple way. So I'm going to show you how to do this in the very long-winded way. Then I'm going to show you something just as correct and way easier. So the reason I want to show you the harder way and do all the integrations by hand is you will reconfront these later on in class. And the answers need to start becoming automatic. So we're going to go through this. This will be your first time seeing it. This is probably one of the more challenging integrals in this class, and I expect everybody to know how to do it. So we can restudy it in review session, not tomorrow, but probably next week we'll do one. And so we can go through this very, very slowly. If you don't learn how to do this integral, I will catch you at least 3 times. So anyway, I will show you an easier way to do it after we do the hard way. Is that enough prompting? So, okay, super engaged. Okay, we'll make this problem harder later on. So our goal is this. Let's do this first. Pi x tilde given x, and I'm going to let you know sigma squared. So we're going to just say this is known. The way I'm indicating that is just putting it on the right-hand side of the bar. If I remove sigma squared from your knowledge base, you don't get to know it, you'll probably estimate it, and probably everything will transform into a t. And it will, and I'll give you lots of different ways to think about that, and 2 such ways are on your homework. So these are the first problems on your homework, I think, is working through this. And you'll get to see some extra distributions along the way. Again, when we're integrating over multiple things, mu and sigma squared, there's lots of ways you can do it. do it in lots of different orders and learn lots of different distributions in between. Okay, we want this. This is our predicted distribution. So we call it a posterior predictive disk. I could probably call it that too. Posterior predictive disk. I need to just let you know what you get to know. So we're just doing this as an exercise. This will turn out to be a normal distribution. When I remove that from you and do the conjugate analysis, it will turn it into a t just like you did before. You'll get to practice all that math we just saw on the board. So good jumping off point. So how do we get this? I'll just say real quickly. So this is kind of how a classicist will argue everything. So very typically is they'll say, wait a minute, where's mu in all of this? I need to do something with mu. In the way that they explained all of this in regression classes, they plugged in x bar for everywhere mu appeared in the equations. A Bayesian doesn't like to do that. They like to integrate over the uncertainty in x bar through its posterior analysis. So it's posterior on mu. So what they'll do is they'll just marginalize. This is the only gig in town for a Bayesian. So they'll write this down, pi tilde mu sigma squared, all of those things. So this is the future. Let me make this a little bit more clear. This is the same f right here for all of these things. I'm going to write it out like this. Xi's come from that. This is a normal density. This f is that normal. So this is the observation of a future observation. We already know that it's normal right here. And I get to know everything when I predict the future. And I even get to know cap x. Very typically, this isn't written into everything. But let's just follow the math, make sure that our probability theory is clear. This is pi mu given x and sigma squared. Let me write it the same way. It doesn't matter, I don't have any intent in which order I write these things. They're just placeholders, but I'll be polite. I'm conditioning on this. I'm conditioning on this. So whatever I condition on here, I got to condition on there. And I'm marginalizing out mu. So this right here, this equation, is the joint distribution for whatever letter we want to attribute to this. I don't know if I should use an F or a pi or whatever, so I'll call it F pi. So because I'm uncommittal, I'm not committing to anything right now. I like them both equally. They both tell us something. So we probably could have used F everywhere, but I just wanted to note they're inherently different things. So x and sigma squared. So I'm just writing down the joint distribution. If I were just looking at some probability theory on the board and nobody taught me anything since probability class, I would say that is true. So this is just like looking at something like this. So pi a is equal to integral pi, or PA b dB. So this whole thing right here. So you could replace those with sums if A and B were discrete and sum out B, but that's just true. If I condition on smiley face here, whatever that random variable is, if I do the same thing here, the equation is the same. So you condition somewhere on smiley, you condition everywhere on smiley. I'm going to work on some life philosophy using that somewhere. That sounds useful. So, same thing, didn't do anything. This is the thing, if I know mu in sigma squared, because everything is IID in this example, again, if I write down the conditioning forms for this equation, how things depend on the past, everything will extend. Right here, everything is IID. So if I know mu in sigma squared, seeing the data doesn't help me. I know everything there is about that distribution. You've already told me mu in sigma squared. What am I going to use x for? So nothing. It's kind of like going to a roulette wheel. and knowing all the probabilities on the board and spinning the wheel over and over and over again and looking at the data and deciding whether or not you should bet on red or black. Since the rolls are independent of each other, it doesn't matter what you've seen before. The only thing you'd be able to verify with the rolls before is whether or not those probabilities that they're telling you are true. You could only verify that. So if we trusted in all of that, the randomization process, rolling the roulette wheel won't help you. So, and everybody that's ever taken a stat class has probably heard that example a bunch of times. So IID stuff, the previous data doesn't help you. So just a quick question. We've answered this before. So I just said, in IID stuff, the data doesn't help you. Is that true? I grappled with this for about 15 minutes as a grad student, thinking, how do we forecast? We always use the data to help us forecast. But if I knew the sampling distribution, the data doesn't help us. That's true. You've said it before.
Well, I mean, I don't remember what it said in the past, but I'm just thinking like we still use the data tool to try to estimate the parameters. It just there's no dependence within the data, so we don't care about like the order, which is sort of where sufficiency and stuff comes in. Sometimes the sample can be, we can turn it into a minimally sufficient statistic.
Or just sufficiency will do it for us. So minimal is just our friend when we go to our computer. We don't even need that. The data is always sufficient. We don't actually know this distribution. We can just write it down. So we're going to need to estimate this mu right here in the process effectively. So we're doing something in the integrand of this equation, and this is weighting our beliefs on mu in the first place. So this is taking our sampling distribution. If we knew mu precisely, we'd have a probability distribution on mu that's 1, a point mass. And this integral would just be an evaluation at a point. But we don't know mu precisely, so we're going to average over our beliefs in mu. So we're taking our sampling distribution effectively and averaging the sampling distribution and learning that parameter. And that's what the data helps us to do. And that's why the data only appears in the weights right here. So the data is there, and the data cancels out of this because you know the parameters, so it just falls out. That's the typical definition of sufficiency or something like that, that it just falls out of the equation. So I already know this stuff right here. Or I already know mu and sigma squared, so this is conditionally independent of the data. That's what this says. So we just get rid of it. So I'm just going to write it down like that, right there. So all we're doing when we're constructing the posterior predictive distribution is coming up with the average sampling distribution. You could think of this as the expected value of this function with respect to that distribution. So this is also an expected value. So that expected value is actually an expected function. So if you like to think about it. So I like to just say it's a weighted average. So I'm just weighting my beliefs in mu and averaging this equation. So how do I want to weight things? Probably by my posterior distribution. That's my best belief in mu. So just real quickly, in terms of our analysis, we've already solved this right here. So let's just make an assumption. We're going to use our reference analysis. I keep putting this word out there without telling you what it is. This is the reference prior, and it's the one most people go running towards. So we're going to use the flat prior on this. So what is that posterior distribution? I'll give you a hint. It's normal. Has 2 arguments. Somebody else with the variance, please. Sigma squared divided by 8. Yep. So that's it. So what is this thing? This is just my sampling distribution. It's a normal distribution. Let's just build in some extra notation and tell us what the random variable is. This one's for mu, right here. This one's for x tilde. And this has mean mu and variance sigma squared. So that's how Bayesian averages. We're not going to plug in x bar into everything. we are going to average over our beliefs in the parameter that we're marginalizing out. So that's how Bayesian does things. For the normal example, it turns out to be the same as what the classicist comes up with. For non-normal examples, we come up with different predictive distributions. So I'll just give you a heads up. Where do Bayesians win in the world? Oftentimes in multivariate predictive analyses, even in things like Poisson predictive analyses, because we know how to just use this formula. So in general, the posterior predictive distribution is just this thing. So in general, we're just going to write down pi x tilde given x is going to be equal to the sampling distribution on x tilde, whatever the original problem specifies, your model, is what most people will call that. So times the posterior distribution, integrate over the parameter set, over the whole universe of parameters. And that's the posterior predictive. So we've just set aside sigma squared so we can make the problem a little easier. So that's how Bayesian predicts, and I kind of love it. So average gives you the ability to bring down variances. So, okay, let's fill this thing out. We'll just write this thing down, and next time we'll buckle up and do this integral. And I'm going to need your guys' help making sure I keep track of everything. So I did it this morning real quickly over my cup of coffee, no mistakes, it was great. So we'll see if I can do it again. So I already know what the answers are, so I usually don't go through everything so long-winded. But we're going to solve this. And then we're going to build up the speed so that you kind of know what the steps, the answers in the little intermediate steps are. So this is going to be proportional to, and we're going to give ourselves knowledge of sigma squared. We'll write it out in terms of sigma squared. I think we're used to recognizing it that way. It doesn't matter. We can flip it upside down at the end of the day if that makes us more comfortable. But this is going to be proportional to our likelihood function for our one data point, our sampling distribution. So that'll look like e to the minus 1/2 x tilde minus mu squared over sigma squared, and times the posterior distribution. So this will look like e to the minus 1/2. This is the distribution on mu minus x bar squared divided by sigma squared divided by n. That's its variance, mu's variance. And I'm going to integrate over mu. I'm going to go from minus infinity to infinity because that's where mu lives. So we've got to do a bunch of work to solve this thing. There is some completion of the square. I'm not going to do that. I'm going to do the same thing and expand the square and teach you to recognize terms. But we basically need to recognize which normal is this. So step one, which normal is the integral? Or is the integrand? So all of this stuff. Then once we solve this equation, keep in mind x tilde is not part of something that we're integrating over. We're going to be able to factorize that thing out right in here. We're going to hold on to it, and we're going to chisel away at the integral. What I can recognize instantly is that I'm going to pull out an e to the minus x tilde squared out of that equation. Once I expand everything and I factorize it out, I already know this is probably a normal because of that, at that first step. So I'm going to pull that x tilde out, get rid of the mu's because I'm integrating with respect to them. Then I'm going to recognize after I solve which normal this is, it's going to tell me which normalizing constant I'm going to evaluate this to. So this is some normal, and so it's going to evaluate to the inverse of some normalizing constant that I can recognize. So I'll be able to understand what the integral is, factorize all the x tilde stuff out, multiply them into each other, And then I need to understand which distribution is that. And it's a normal as well. So we're going to play the game, which normal is it, twice. So, and they're probably not super obvious all the way through the calculation. So step 2. So this is which normal in mu. And then we're going to ask the question after we integrate. We'll ask which normal is everything in x tilde. If you can do this, you can do it in high dimensions as well. And I'll teach you how to do that in a few weeks' time, probably after the winter. So same game, that expand the square. Can I recognize it in expanded form? Can I figure out what its normalizing constants look like? We're going to keep doing that over and over and over again until we recognize the answers. So anyway, same thing, expand, look at the quadratic term, look at the -2 linear term to answer the questions, then we can recognize what the normalizing constants are, then we can combine everything and do the exact same thing. Which quadratic term? Now we're going to look for the quadratic at x tilde, recognize its variance, then look at the -2 linear at x tilde, recognize its mean. So see if you can do all of that right there. So this integral is possible to do using the knowledge of the normalizing constant. If you didn't know any of that, how would you integrate this? So if you're just in an engineering class, not a stats class where they told you where everything added up to 1 in some special forms, how would you do that integral? So I'll look for an answer next time, unless Sam wants to give us one.
I was just gonna say maybe try the polar trick.
It's the polar trick. Yeah, that's the only way I know how to do it. I'm sure you could do it in complex, but it's essentially the same by mapping it into polar. That's it for now, you guys. We'll come back next time, do this integral. I think no quiz this time around, because we'll just want to jump right into this. I don't want to fry you guys right beforehand.